This tutorial is on sequential UDPs. There are two types of sequential UDPs. One is a level sensitive, the other is a edge sensitive. Level sensitive, it is sensitive to input levels. Edge sensitive, it is sensitive to edge transitions on inputs. So here edge behavior can be done. Here only level behavior can be done. In a description where only we do level sensitive behavior, it's called level sensitive sequential UDP. In a description where we can have even edge sensitive behavior, it's called edge sensitive sequential UDP. In subsequent slides, we will see with examples. Sequential UDPs have the differences when compared with combinational UDPs. Those are: output of sequential UDP is always declared as rich. In a combinational UDP, we declare output and then input. That's it. But here, extra declaration is required, that is rich. This extra, though we are declaring with a keyword output, that identifier needs to be redeclared with a keyword rich. Initial statement is used to initialize output of sequential UDPs. Initial procedural construct we will be using to initialize output of sequential UDP. So, sequential circuit initial state must be known. So, as a designer will initialize the output of the sequential circuit. So that initialization is done with the help of initial statement. Initial is a procedural construct. The format of a state table entry is slightly different. That is, look at this: all inputs colon current state colon next state then semicolon. Whereas in a combinational UDP, all inputs colon output then terminate with a semicolon. Here in this case, the extra state current state is not actual output. Next state is a actual output. Sequential circuit behavior will depend not only on the current states, it also depends on the sequential circuit behavior. Sequential circuit behavior, it depends not only on the inputs, it also depends on the current state. So that this next state is a actual output. For example, you have a T flip-flop. It toggles. If the current state is 0, next state will be 1. Now this 1 has become the current state. Upon the arrival of the next clock, this current state 1 will become 0. That is, next state is a 0. So that's why this current state is required in describing sequential UDPs. So this is the additional field in sequential UDP. Input specifications of state table entries can be in terms of level transitions or edge transitions. Input specifications here. These input specifications may be level transitions or maybe edge transitions. So this is what we have here: level sensitive, edge sensitive. If input specifications all are level transitions, then it is a level sensitive sequential UDP. If input transitions here having some this edge transitions, then it is called edge sensitive Sequential UDP. So input specifications of state table could be level transitions or edge transitions. Current state is the current value of the output register. That is what I said. If T flip-flop is currently having a 0, it's the current value of that 1-bit register T flip-flop. Now next state is computed based on inputs and the current state. So here the input is a clock and the current state is a 0. So next state will be 1. It toggles T flip-flop. So next state is computed based on inputs and the current state. Next state becomes the new value of the output register. Now this 1 has become the new value of the output register. Let us look at this example. This is the level sensitive sequential UDP having a clear, clock, D and Q. D, clock, clear. 3 are inputs, Q is a output. So the behavior is like this. If the clear input is 1, the output Q is always 0. If clear is 0, when clock is 1, as long as clock is 1, Q will be assigned with D because it's a latch. If clock is 0, Q retains its value. Clock 0 and clear must be 0. Then this Q will retain its value, previous value, whatever. So this is the behavior of this sequential UDP. This sequential UDP is a level sensitive. No transition. We're not talking about the transition, what effect will take place on the output. No. We are talking about the level. That is 1, clock 1, like that. So how do you describe this behavior in a Verilog? So Verilog description of level sensitive UDP. So you know any UDP will start with a keyword primitive, and this latch is a user defined name, first output and then inputs. So here is a declaration. Output Q. This output must be redeclared with the keyword reg Q, and then input D, clock, clear. So this output must be initialized to a known value in a sequential circuits. So that we are doing with the help of procedural construct initial. Remember, only one initial statement is allowed. Initial Q is assigned with 0. Now state table. Within table and end table will be having the behavior description, hardware description. So this line is commented. This is for our reference. Without this line also one can describe this behavior if one could able to ensure in his mind that these entries are for particular input and these entries are for particular input, not to mix up. So this is for our reference. Anyway, this will be ignored by the compiler because of single line comments. So better to have this reference. Now D value is don't care here. It could be 0, 1, X. Even clock is don't care. In that case, if clear is 1, the output will be 0. Whatever the current state is. Maybe 0, maybe 1 here. Whenever clear is 1, this is 0. This is 0. When D is 1, when clock is 1, clear is 0, this D is seen on output. Whatever the current state is, output will be 1. That is, whatever the current state is here, maybe 0, maybe 1. If D is 1, when clock is 1 and when clear is 0, this 1 is seen on output Q. So that is what here. When D is 1, when clock is 1, when clear is 0, this D is seen on output, whatever the current state is. Similarly, when D is 0, clock is 1, clear is 0, this 0 is seen on output, whatever the current state is. Now there is no clock, there is no clear. So output will not have any change. No change in output. Whatever the current state, that same state will be retained here. So in output we cannot show with this don't care. Output must be with known value 0, 1 or no change, like this dash. So whatever the current state, same state is maintained. How we represent that one with dash, no change. So we have completed our description. Now end table and then end primitive. So this is the example for level sensitive UDP. So here is a pointer, ANSYS style port declaration for sequential UDP. This ANSYS style port declaration is also known as 2001 language style because some amendments have been done in the year 2001. So those are sequential UDPs can include the reg declaration in the port list. We know in a module we can write within parenthesis type declaration as well, output and then output identifier, input keyword and then input identifiers, separating them with a comma. So here a reg declaration can be done within the port list, the way you see reg declaration. They can also initialize the value of the output in the port declaration. This is the initialization. In the port list declaration itself, we can initialize this one, like this directly assigning. So what we are doing here is within port list area, we are declaring event type and reg output is redeclared with a reg. Even assignment is done directly like this. So this avoids all this declaration separately. Output Q, reg Q, and then initial procedural construct and initializing that output. So these steps are eliminated by directly doing or declaring them within the port list area itself. So this style is known as ANSYS style port declaration. Let us look at this example, edge sensitive sequential UDPs. Here this clock is negative edge. This is the input D and output Q, and this is a clear. This clear is asynchronous. If we are representing this is clear here, it is asynchronous. In parallel to clock, if we represent clear, that is synchronous. Now these are the specifications how circuit behaves. This figure, edge sensitive D flip-flop with clear. This circuit behaves in this way. If clear is 1, the output Q is always 0. If clear is 1, the output Q is always 0, irrespective of clock, whatever, negative edge or positive edge. This is of course working for negative edge. Though negative edge is there, but as long as clear is 1, the output Q will be 0. If clear is 0, the D flip-flop functions normally. That is, whenever the negative edge comes, this D is seen on Q. On the negative edge of clock, that is the transition from 1 to 0, Q gets the value of D. If clock transitions to unknown state or on a positive edge of clock, don't change the value of Q. If clock transition is taking place to unknown, then if clock is transiting to positive edge, then we shouldn't change the Q value. It has to retain the previous value. If D changes when the clock is steady, clock is not having any changes in that, no transition is taking place, it is steady. So it means it is there in a negative logic, logic 0, it is in that logic 0. Or if it is there in logic 1 state, logic 1 state, no transition. So no transition is taking place, steady clock. Then whatever the changes that are taking place on D will not have any effect on output. So it means Q holds the previous value. So this is how this circuit is working, D flip-flop. So we have to describe this functionality, this behavior in a Verilog. Before describing this behavior, D flip-flop behavior, we have to have knowledge of this. What is this parenthesis? What is this 1 0 x1? So we call them edge transitions. So within parenthesis, if you are writing 1 0, means transition is taking place from logic 1 to logic 0. So this is a negative edge transition. So this is negative edge transition when within parenthesis if there is 1 0. If 1x, x is unknown, so it denotes a transition from logic 1 to unknown state. 0 question mark, 0 to don't care. It may be 0, it may be 1, it may be x. It denotes a transition from 0 to don't care. So chances are there, if it is going from 0 to 1, then it is a positive edge. That's why we call it as a potential positive edge transition. Similarly, if x happens to be 0 or 1, if it happens to be 0, in that case transition is taking place from 1 to 0. No? That's why this can be called as a potential negative edge transition. The way we are calling this one as a potential positive edge transition, this can be termed as a potential negative edge transition. Now look at this. Within parentheses, if we are having question mark, it denotes the transition in a signal value 0, 1 or x to 0, 1 or x. So any transition. So these are the edge transitions. Now let us look at the description of this D flip-flop with clear. So we are defining with a we'll start with a keyword primitive. Edge underscore DFF is a user defined. This is a ANSI C style port declaration. Within parentheses we are declaring type. We are initializing the output Q. So reg also been used within the port list area. So this is a ANSI C. We have seen what is ANSI C. ANSI C style port declaration. If this way if we are doing within parentheses output reg and this output been initialized and then input keyword been used, so this is called ANSI C style port declaration. Now here not required separately again, type declaration, reg and initial procedural construct to initialize the queue not required. We have done it here. Directly state table. So state table will start with a keyword table, and then as been said, these are for our reference. Whatever the D, whatever the clock, if clear is 1, then output will be 0, irrespective of your current state, whatever the current state is. If D is any value, clock is any value, clear is transiting to 0 from 1 to 0 means negative edge. So it will not have any effect on your output. So previous value whatever, same value will be retained irrespective of your, whatever the current state is, same current state is retained here. Dash indicates no change in output. Now D is 1, clock is transiting from 1 to 0, means negative edge. There is no clear. So this D is seen on output. Whatever the current state is, next state will be 1. Now the D is 0, your clock is transiting from 1 to 0, means negative edge, no clear here, whatever the current state is, but this 0 is seen on output. D is any value here, it could be a 0, it could be 1, it could be X, don't care here. Clock transiting from 1 to unknown state. In the behavior, it is being said, if this is clock is transiting to unknown state, don't change the output. In the description of this circuit, if clock transitions to unknown state or on a positive edge of the clock, don't change the value of Q. So according to that description, this Q is having no change, output is not having any change. Next state. Now D is don't care, clock transition is taking place from 0 to don't care, so it is a potential positive edge, so that's why no change in the output. Now clock is transiting from unknown to 1, so this is also a potential positive edge, so this is also, there will not be any change on the output. Now any transition may be taking place on input. This is don't care, maybe 0, maybe 1, maybe X, no transition at all. Anyway, clear is 0. So this will not have any effect on output. So no change on output. So that's how we have to describe our behavior of the hardware. So we have done with our description here. Now end table and then end primitive. So this example is for edge triggered UDP. Similarly, you can try for any other flip-flop, JK flip-flop, T flip-flop, please try. So important points to remember here are, we have to completely specify the UDP by covering all possible combinations of transitions and levels in the state table for which the output have a known value. So that is, all possible entries must be done here for which there is a known output, that is 0 or 1. This dash is a previous state, whatever the previous state is, in that no change. So this is valid here. So all possible cases we have to cover. If we don't cover all possible cases, then this output will be a unknown state. So otherwise some combinations may result in an unknown value. This is one point. The other point is, only one edge specification is allowed per table entry. Per table entry, this is one entry, this is another entry, this is another entry, like that. So per entry only one edge transition. Look at this entry, no edges here. Here only one clear, that is transiting. Here only clock is transiting. Here clock is transiting. Here clock is transiting. In this case, only D is transiting. So transition must be on only one identifier. So more than one, they cannot have transition like this. Here some input that is transiting from 0 to 1. Here another input that is transiting from 1 to 0. So like that, two transitions are there in a row, which is illegal. So Verilog will not permit that one. So this is another point that we have to remember. Let us look at this example, 4-bit binary ripple counter example. So we want to develop or build ripple counter. In order to build a ripple counter, we are using T flip-flop. Since it is a 4-bit, so we need 4 instantiations of T flip-flops. This instantiation name is optional here. Without this also you can do. So now first flip-flop's output is acting as a input clock to the second flip-flop. Second flip-flop's output is acting as an input to the third flip-flop input. Second flip-flop's output is acting as a clock input to the third flip-flop. Third flip-flop output is acting as a clock input to the next, that is final flip-flop, fourth flip-flop. This is how the ripple counter behavior is, right? So we are instantiating simply, we are not writing any behavior here for counter. We are making use of T flip-flop. This T flip-flop is developed using UDP, not module. So this is how we are using instantiating a UDP, sequential UDP. Let us look at this T flip-flop UDP now. T flip-flop with UDP. So here any UDP will start with a keyword primitive, and then T underscore FF is a primitive name, and then this is ANSI style. We are not initializing Q because this Q is initialized here in the description. No initialization of Q. TFF, that is T flip-flop, will be initialized with a clear signal. Within table and end table, hardware description. Here, whatever the clock is, don't care here. It is no transition actually. We can say it's a level sensitive. When clear is 1, irrespective of your current state, whatever the current state is, your next state is 0. This is asynchronous behavior. You try for synchronous behavior. Now, clock is don't care again, no transition here. When clear is from 1 to 0, that is transition is taking place from 1 to 0, means negative edge. This will not have any effect on the output. So output will not have any change, no change in the output. So this is how we represent for no change. Irrespective of your current state, whatever the current state is, in that current state there will not be any change. Because no clock, no clear. Now the clock transition is taking place from 1 to 0. This is a negative edge. If you look at your design T flip-flop, this T flip-flop is working for negative edge. So 1 to 0 transition when taking place, that is negative edge. When clear is not there, if the current state is 1, then next state will be 0. It toggles. T flip-flop behavior is, if current state 1, next state will be 0. If current state 0, next state will be 1. It toggles. Next entry is, if you look at this one, again transition is taking place from 1 to 0, that is negative edge. Clear is not there. When current state is 0, next state is 1. It toggles. Now next entry is 0 to don't care. So it is a potential positive edge. So our hardware is working for negative edges. That's why here, since this is a positive potential positive edge, this will not have any effect on our output. So no change. Whatever the current state, that current state is retained. So we have completed our description for the hardware. Now end table and then end primitive. So here what I was telling while ago, you try for synchronous clear. So for that clue is important point. This is the clue for you people to design synchronous T flip-flop. Level sensitive entries take precedence over edge sensitive entries. Level sensitive will take precedence over edge sensitive entries. Means in a Verilog, first edge sensitive cases are processed first, followed by level sensitive cases. When level sensitive and edge sensitive cases specify different output values, the result is specified by the level sensitive case. When level sensitive and edge sensitive cases specify different output values, the result is specified by the level sensitive case. So level sensitive has overridden the edge sensitive. That's why level sensitive got a precedence over edge sensitive. Look at this example. In our case, in this example, we have this entry where question mark, that is clock is a question mark, clear is 1, q is question mark, and next state, present state is question mark, next state is 0. So clock, clear, current state, next state. This is a level sensitive. But this entry is not there in table where negative edge transition is taking place, where clear is 1. The current state is whatever the current state is. Next state is x. Because since this entry is not there, it will give us a x unknown value. So this we have seen for all cases we have to have entries, otherwise simulator will return x unknown value. Let us say since this entry is not there in our table, uh, for a given time interval, if we are writing negative edge, giving a negative edge, and clear is 1. So what happens is it will assess and it will return a value unknown. So first edge will be processed. Edge sensitive cases will be processed first. Later on, this entry is there in a table, so it will process even this one. Output is 0 here. So according to the compiler design, level sensitive entries will take a precedence over edge sensitive entries. So it will return a value 0. Level sensitive will take a precedence over edge sensitive. It will return a value 0. So that's how it has become a asynchronous clear. So if you focus on this point, that is level sensitive entries take precedence over edge sensitive entries, you can design a synchronous clear. Again, I am repeating this one. Here, this entry is not there in table. You are trying to test, suppose this T flip-flop. So, what is first of all asynchronous clear? Irrespective of your clock. Suppose your design works for a negative edge of the clock. So, what is synchronous? First, clock edge transition must be there. Then it will check whether clear is 1. Suppose say active high clear. Then only output will be made to 0. That is synchronous. In asynchronous, though negative edge is there, or it may not be there, negative edge. If clear is 1, then Q is made to 0. So it is irrespective of your clock. If clear is 1, then also output will be made to 0. So not necessarily that it has to synchronize with clock. There may not be a negative edge transition, but clear is 1, but still Q is made to 0. So that is asynchronous clear. So here this entry is not there in the table. So you are trying to test that behavior of the T flip-flop what earlier here we have this one. So in that case, for a given time interval, suppose you are giving a here edge transition, that is negative edge transition clock, and clear is 1. So what happens then? Since this is not there in a table entry, but according to the design of the compiler, first edge sensitive cases will be processed. Edge sensitive cases will be processed first. So it will process anyway for this, but it will return an unknown value x because this case is not there. Then it will process a level sensitivity. So this case is anyway we have stated. So it will return a value 0. Finally, the final value of the output is decided by the level sensitive entry, because the compiler design is such that level sensitive entries take precedence over edge sensitive entries. That's why output will become 0. So this is the clue. Very neat and clear clue. You have to think over this one. Then you can model this T flip-flop for synchronous clear. So this ends our tutorial. Thank you so much.